Hey everyone, welcome to the sixth lecture in our series on imitation learning. I'm Sanjivan Chaudhary, a research scientist at Aurora and soon to be assistant professor at Cornell. Today, we'll talk about a class of imitation learning methods that try to recover the underlying reward or cost function that a human uses. We'll look at the problem from two different perspectives. Number one, by treating the human as an optimal planner, and number two, by treating the human as a stochastic process. And in the end, we'll see that both of these converge at a unified game-theoretic framework. So let's get started. Let's begin by looking at the application of off-terrain navigation. For example, you have an all-terrain vehicle, an ATV, that can drive over all sorts of terrain. And the question is, what is a good terrain to drive over and what type of terrain should we avoid? So, one kind of terrain class could be driving over waters, which is probably not a good idea. The other could be flat grass, which seems nice. And the third category could be rocks, which is less preferred to grass. And any given time, the robot faces a terrain with all three components. We then hire an expert ATV driver who then drives around and gives us a bunch of demonstrations. You can see here they're preferring to drive mostly over grass, but are okay going over rocks as well. So how do we formalize this problem of their preference of preferring one type of terrain over another? Well, as we've done in the past, we are going to formalize this by defining an MDP. So if you recall, an MDP is a tuple of state, action, transition, and cost. But in this setting, we're going to assume all three state, action, transitions are known, and it is the cost function that's unknown. Now let's assume, for this example, that the cost function is in fact a linear function, and it's a linear sum of penalties of being at different terrains. So the cost function is W1, a weight W1, times does the state belong to water, plus W2 times an indicator function that says, does the state belong to grass? Plus W3 times an indicator function of, does the state belong to rocks? So you're essentially learning penalties for being in different terrain. More generally, you can think of each of these indicator functions as being a feature function that maps state and action to features. And compactly, we can write the cost function as W transpose times F. Now, given that we have a cost function, we can typically call a planner that solves for a minimum cost trajectory. So it performs an argmin operator over a sequence of actions that minimizes the total cost. Again, assume that dynamics here are known and maybe deterministic. Once you do that, you trace out a trajectory of state, action, next states, and so on. And that's pretty much the model. Now, let's see how different combination of weights can give us different trajectories. For example, let's say you have a trajectory that drives straight through the water and reaches the goal. It's likely, if you look at the weights that produce such a trajectory, you have to assign a high weight to go on grass and rocks and low weight on water. On the other hand, if you penalize water and put less weight on grass, you'll have a trajectory that takes a long detour and goes on the grass. Similarly, if you put low weight on rocks, you'll have a trajectory that prefers going over rocks. So the objective is we're looking for a magic combination of weights that penalizes everything just right, so we produce a trajectory that matches the demonstrated human trajectory. So our objective is that given optimal demonstrations psi human, which you can think of as a sequence of state action pairs, find a cost function that generates it. Find a W vector. Also, quick notation, we'll often be using the notation c theta psi to note the cost of a trajectory. Now, this problem is also known in literature as inverse optimal control. It's also known as inverse reinforcement learning, cost function learning, and so on. So how should we go about solving this problem? Well, one way to think about this problem is to think of it as just a very, very large multi-class classification problem. How so? Well, think of each trajectory that the robot can choose as being a class. There are many, many trajectories that the robot can choose that go through all terrains, and the goal is to pick a trajectory that matches what the human would do. So if you think of this as a classification problem, what is a data point? Well, each data point is a MDP, a scenario that the robot visits, as well as a demonstration, what the human does. So each data point is phi I, which denotes the MDP, and xi ih that demonstrates what the human would do in this setting. And we get n such data points. And our goal is to find a theta such that the cost of the human trajectory in the MDP is smaller than the cost of any trajectory in that MDP. And this must hold for all data points. So in a nutshell, every trajectory is a class, which makes it a very large classification problem. Let's begin by thinking about the linear setting. So in the linear setting, every MDP phi induces a feature map fi for that particular MDP, that particular configuration of waters, rock, and sand. So the cost of a trajectory in an MDP is simply W transpose of the feature map, which is the sum over per state action costs. So our goal is to find a W vector such that W transpose times the feature map of the human trajectory is less than W transpose times the feature map of any other trajectory for all data points. So great, the optimization that we have written down appears to be a linear program, so can we just send it to a linear program solver and have it solve the problem? Unfortunately, this totally fails. Why? Check W equals to 0. It appears to satisfy this optimization problem, so we have a trivial solution. So that's not good, but this is a familiar problem, and typically we use the notion of a margin to get around this. So we now want the human trajectory to be less than the learner trajectory by a margin, where you can think of the margin being a 0-1 loss. 0 if the trajectory exactly matches the human, and 1 elsewhere. Okay, so good, but there's a slight hiccup. Notice that there's exponential number of constraints, because for all possible trajectories, we have this sort of inequality constraint. And that can be intractable to deal with. There's an easy fix. Don't look at all the trajectories, just look at the minimum cost one, right? So you can verify that the inequality is the same if you pick the trajectory that has the minimum margin augmented cost. So it seems like we are done. No, this too fails. This time the failure is a little bit subtle. So let's pretend we have a weight vector W prime such that the human trajectory is a tiny bit cheaper than the learner trajectory. So not more than the margin, but just a bit cheaper. If we now just crank up the weights by a ridiculous amount, we can solve this problem. In other words, it seems like this problem is ill-posed and has sort of multiple solutions. You can always make the weight vector arbitrarily higher to just satisfy this inequality constraint. This should remind you something from ML 101. SVMs. And if you remember then, the solution was to break ties was to maximize the margin. So we can do the same thing here. Maximizing margin simply means minimizing the norm of the weight vector W. Subject to the set of constraints, we'll also add in an extra select variable and minimize that. And voila, we end up with this very SVM-like problem. And it's appropriately named maximum margin planning. It's a paper by Ratliff et al., which I highly recommend checking out. And this approach can also be extended from linear to a class of nonlinear cost functions. So this approach is called Lurch. It's also by Ratliff et al. And the fundamental idea is you're searching this time for a cost function, and you're minimizing the difference of the cost of the human trajectory versus the best cost produced by a planner on the margin augmented cost functions, plus a regularization on the cost. A quick aside, in general, there's three ways to sort of lift a linear objective to a nonlinear objective. The first is by using boosting. Second is by kernel gradient descent. And the third is by sort of a parametric functional gradient descent, for example, deep learning. And we'll be talking about the third approach here. Okay, so let's take the same example we were seeing before, where we have some demonstrations of the human going over some grass and some rocks. And let's talk about what the Lurch algorithm looks like. So the Lurch algorithm iterates over n data points. Recall that each data point is a pair of MDP, phi I, and human demonstration psi I h. Now for each data point, we are going to compute the optimal trajectory xi I star. How? We'll do this by solving an optimization problem where we are finding a trajectory that has the minimum cost minus the margin. And typically you do this by calling a planner. Now we are going to update our cost function parameter theta by taking the gradient of the human trajectory and subtracting from it the gradient of the optimal trajectory, and also taking the gradient of the regularizer. Basically, bump down human trajectory and bump up planner trajectory. Okay, so let's run this algorithm in our example. Let's say we began with, water being very cheap. So we plan a trajectory that goes straight through the water. Now we are going to bump up water, since we don't see it, and we're going to bump down grass and rocks because the human trajectory goes through grass and rocks. Okay, so we end up with a new set of weights where rocks are weighted slightly lower than grass. So naturally the planner is going to go through the rocks. Again, repeat the same process. Bump down rocks, bump down grass, bump up rocks, and finally you end up with a set of weights that produces exactly the same trajectory that matches human. And we've solved the problem. But wait, I spoke too soon. There is yet another new class of problems that this method doesn't do so well against. That is when experts are suboptimal. Recall that when we formalize the problem, we assume experts are optimal, but in the real world, that is not always the case. So let's take this sort of pathological example. We have a terrain where there is a big stretch of water, and the top half of the terrain is all grass. And the bottom half of the terrain is all rocks. Now let's pretend we receive a demonstrated trajectory that goes through the grass, but that takes a longer detour, presumably because the expert wanted to avoid going near the water. We would call this an example of an unrealizable expert. Formally, there does not exist any cost function in our cost function class for which the expert trajectory is optimal. So what would Lurch do in this setting? So once again, let's go through the exercise. Let's begin with a set of weights where water is cheap. Naturally, the planner drives straight through the water. Can we bump up water, bump down grass, and now we produce a trajectory that kind of hugs the surface of the water. Because this is the optimal trajectory when the weight of the grass is lower than all other weights. And in some sense, the optimal trajectory will never waste any time doing unnecessary detours. So what does Lurch do? Lurch still sees that the human trajectory sees more grass than the planner and continues bumping down the weight of grass. And as a result, the same trajectory is produced because, of course, the optimal trajectory will never change no matter how small the weight of the grass is. So we see that in this setting, the Lurch gradient never goes to zero. It's always non-zero. And as a result, the weights keep running away and you don't get any convergence. So how do we make the algorithm work for suboptimal experts? Well, we'll fix this with a very simple idea. Instead of trying to find a cost that makes the expert look optimal, can we instead think of the problem through a probabilistic lens? Can we think about trying to find a distribution over trajectories that, in a sense, match what the expert is doing? So can we make this into a distribution matching problem? More formally, we would like to find a distribution over trajectories such that the expert cost in expectation is equal to the trajectory cost in expectation for all possible cost functions in our cost function class. In other words, we are looking for a distribution that makes the expected expert look like the expected learner. It's a weaker equality condition. So we'll call this paradigm probabilistic modeling via moment matching. Okay, so let's return back to the linear setting where the cost function c theta was w transpose f. W is a set of weight vectors, and f1 to fk are a set of feature maps. This time, we're not going to assume human is optimal. Instead, we're going to assume that they are drawing trajectories from an unknown human distribution, right? So if you take a look at that pathological example, we're going to assume that the expert is just giving us samples from this sort of unknown distribution, right? Our goal will be to find such a distribution. And how will we check if it matches? Well, we are going to check that the distribution agree on expected moments. So by that I mean they agree, you look at each feature map, fk, and they agree that the expected feature values match up, right? So on the left-hand side, we have the expected feature value of the human. On the right-hand side, the expected feature values of the expert. And for all possible feature mapping, these must agree. This is called moment matching. This simply means look at the average time the expert spends on grass, for example, and match it to the average time the learner spends on grass. Similarly, look at the average time the expert spends on water or on rocks and make sure the learner matches that. The cool thing is if you do this, any linear combination of these constraints are also matched. In other words, if all moments match, the expert cost must be equal to learner cost for any cost function in your linear cost function class. Which is a pretty powerful guarantee. But as always, as the theme of this lecture, there's going to be a problem. So what is the problem? Let's say we want to match moments of a particular feature f1, and we are given the human's histogram of feature counts. That is, how often does the human take on particular feature values? Our goal is to find a distribution p psi that matches the average feature counts. Now there are multiple possible choices of p psi. One choice is to simply pick the empirical distribution. Wherever you see the histogram bars, pick a distribution that has peaks there. The downside of this is you have zero mass on feature counts that you don't observe, which may not be correct. Another extreme choice is to pick a distribution that has a peak right in the middle and has no mass anywhere else. It seems odd, but this distribution also matches the average feature count because it's right between the two peaks, two histogram peaks. But again, it has zero mass where you have actually observed data. The third choice is to have a probability distribution that's more spread out. And the problem is, which of these three choices is correct? So that's why this method is ill-posed. And to break ties, we have to introduce an objective function, which is we are going to maximize the entropy of a distribution while matching moments. That's how we're going to pick ties. We're going to pick the maximal entropy distribution. So this idea is an old and foundational idea. It's the idea of principle of maximum entropy. And I highly recommend reading this paper by Jaynes in 1957 that justifies why you might want to do that. But the high-level idea is you want to pick a distribution that's least committal. It's almost like an Occam's razor argument in the space of distributions. There are many justifications for why this is useful. So we write down our formulation once again. We want to maximize entropy subject to matching the empirically observed moments. So on the left-hand side, you have the expected feature counts on the learned distribution. On the right-hand side, you have the expected feature counts of the expert that you observe empirically. For example, you might get a data set of the expert's feature count. For example, the average time they spent on water or the average time they spent on grass. And you get these values of 0.0, 0.8, and you're supposed to learn a distribution that matches these average feature counts while having maximum entropy. Now, we won't go through the full solution, but provide a sketch here, but I highly recommend working it out yourself. So the first step is to write out the Lagrangian of this constraint optimization. And the Lagrangian is the objective minus the Lagrange multipliers times the equality constraint. You then take the gradient of the Lagrangian with respect to the primal and the dual variables, set it to 0, and solve. The solution is really elegant. So its solution says P of xi is equal to the exponent of the negative Lagrange multiplier times the feature count, and you normalize this. Look at this expression for a bit. Think of this Lagrange multipliers, lambda k, as being cost function weight wk. Then the equation says the probability of a trajectory is proportional to exponent of the negative cost. In other words, the lower the cost, the higher the probability, which is a profoundly beautiful, intuitive equation that drops out of this formulation. So finally, the final step is to plug this solution back into the optimization problem to solve for these optimal Lagrange multipliers. And you end up with an objective function that says maximize the log likelihood of the human trajectory given this probability model, which is the typical objective function one uses in generative modeling. So it's really elegant how this maximizing entropy gives rise to this intuitive probability expression as well as intuitive objective function. So taking a step back, this method can be generalized to the nonlinear setting as well, and it's referred to maximum entropy inverse optimal control. So now you're solving for a general class of cost functions theta, where you're minimizing the negative log likelihood of human demonstrations, where the probability function is proportional to x of negative cost of a trajectory. So that's your model. And for more details, I recommend checking out a paper by Zbot et al. Called Maximum Entropy Inverse Reinforcement Learning. And for more details, I would recommend reading Brian's thesis as well. Okay, so let's build some intuition. If we plug in the model in the objective and write it out, we'll see that the objective looks like minimize the cost of the human trajectory plus the log partition function, log z theta, If you look at z theta, it's simply the integral of exp of negative cos. So this expression looks a lot like log sum exp, which is also known as the soft min operator. So the objective looks like expert cost minus a soft min of the learner cost. So the algorithm is very similar to Lurch. We are iterating over all data points, and in each iteration, we are going to sample trajectories from our probability distribution. Note that we're not calling an optimal planner anymore. Instead, we're calling a soft planner that gets us lots of low-cost trajectories, typically using MCMC methods or maybe Laplace approximations, or pick your favorite sampler. Then we're going to update our cost function parameter theta by bumping down the gradient of the human and bumping up the gradient of these samples. It should remind you a lot of the EBM methods that we saw in lecture 1, where you want to make the human look cheap and all other trajectories look expensive. Let's take a look at what the algorithm does in this pathological example. So we begin with weights. Let's say we begin with weights that are all equal for all terrains. Notice that all trajectories have low cost, so we're going to get trajectories from everywhere, through the lake, through the rocks, through the grass. Gradient will then bump up water, bump up rock, and really push down grass, right? Now, because the weight of grass is really, really small, if we sample from this distribution, it's almost as if we're getting the same trajectory over and over again, because the distribution is really skewed to be heavily concentrated about the low-cost trajectory. This is where maxent becomes useful. Maxent is now going to bump up the cost of grass, right? As a result, making the distribution look more flat, less skewed, and we're going to see all these sort of suboptimal trajectories that are being sampled, that end up matching, end up looking a lot like the human trajectory, and hence matching moments. And so this sort of process, instead of calling an optimal planner, calling a sampler, gives us convergence, and we are able to match the expert distribution. And this is really great because for any experts, optimal or suboptimal, we are able to recover cost functions. So as we come to a close, let's compare the two methods we saw head to head. The max margin planner, the update rule looked like bump down the cost of the human plan and bump up the cost of the plan produced by the learner, which happens to be the optimal plan xi I star. How does this contrast with maxent? Maxent, again, we are bumping down the human plan, but we are bumping up the cost of samples that are low cost trajectories, right? Instead of the optimal plan, we're doing a soft min operation. That's the only major difference. Also recall that both algorithms require to break ties. So in max margin planning, we maximize the margin to break ties. For maxent control, we maximized entropy to break ties. Finally, on max margin planning, we were regularizing the costs. We had an L2 regularization. In max entropy planning, we were regularizing the planner. We had an entropic regularization. So finally, we used an optimal planner for max margin, and we used a soft planner for maxent. For example, soft active-critic. But as we will see in later lectures, both of these methods are at heart solving the same underlying game. The game is as follows. There's two players, a max player and a min player. The payoff is cost of the human trajectory minus cost of the generated trajectory. The min player proposes trajectory, and the max player proposes cost function. This is the fundamental imitation game that's going on. So max margin, from this perspective, is playing no regret with the outer player and best response on the inner player. And maxent is playing no regret on the outer player and an entropic regularization best response on the inner player. And in fact, the performance of both of these algorithms can be explained purely from this game theoretic viewpoint that we'll explore in future lectures. So we're now at an end. Let's recap the key challenge that we explored in this lecture. We looked at the problem of learning cost functions that explain human demonstrations. We looked at two main methods to tackle this problem. Method one, we tried to recover costs that make the expert look optimal. The way we did this is via maximum margin planning, which bumped down the cost of human trajectories and bumped up the cost of optimal plans. The problem is that it could not tackle suboptimal experts. So that led to method two, where we instead learned a distribution over trajectories that matches all cost function moments, using the principle of maximum entropy. We saw that this could actually deal with any expert distribution. Finally, we saw that both methods are in fact solving the same underlying game but in different ways. I'll leave you with this thought that the running theme of this lecture is that imitation learning is all just a game between a discriminator and a generator, where the discriminator is either the cost function or the advantage function, and the generator is either the planner or the policy. With this, we're at an end. See you in the next lecture. Till then, be well.